And I should have been recording. Okay, so the mean value theorem guarantees to us that there is a value where the area is equal to the area under the curve equals the integral. So let's look at the mean value theorem. F is continuous on the closed interval. It's still 4.4. F is continuous on the closed interval AB. Then there exists a number C on the closed interval such that the integral from A to B of f of x dx is equal to f of c times b minus a. This is the mean value theorem for integrals. F of c here is called the average value. F of c is our average value. If we think about this geometrically, let's say that we had some kind of function here. Maybe it looks like this. And we're going from A to B. There's some value in here, C. Don't know exactly where it is because of what I've drawn. But that f of c times b minus a would equal the area under the curve exactly. F of c times b minus a.
How do you find f of c?
You'd have to have a value. You'd have to have something for the function. I'm going to show you in a minute how to find it.
What did you just say?
He asked me how to find f of c. We'll see that in a minute.
I was going to say, what did you just say right there?
That this f of c times b minus a gives you the area of the rectangle. F of c right here, this is f of c. And if we take f of c, height times width, we get the area of the rectangle. And there's some value of c in there somewhere that this is equal to the integral from a to b of f of x dx. That's just the mean value theorem for integrals. Yes, underneath the curve from A to B. From A to B.
So you just take the average of b and a to get c?
Not necessarily. We're going to look at that in a minute. All right. So when we think about average, just in general, when you first started learning about average, what were you doing?
You were adding together,
Adding and then dividing. You were adding and then you were dividing. If you wanted to find out what your test average was, you'd add your test up and divide by the number of tests, and that would give you average. Remember, when we find an integral, if we think in terms of Riemann sums, what are we doing? We're adding.
You're adding different intervals.
If we're thinking of Riemann sums,
You're adding like individual like integrals that are equal in value to each other.
You're adding different rectangles.
we're adding areas of rectangles. It's accumulation. We can sometimes think of an integral as an accumulation. And so we said that f of c is the average value. There is an average value theorem. The average value for a function we get by taking 1 over b minus a from a to b of f of x dx. And so this is going to actually be equal to f of a minus f of b minus f of a over b minus a. It looks a little familiar. This is the derivative of this. This is the top part is the fundamental theorem of calculus. When you integrate, that's just what we did on the homework. F of b minus f of a, that's the fundamental theorem of calculus.
AB.
So it's just like derivatives.
Average value. This is the derivative of f.
Wait, what'd you just say? What is the derivative? The left side is the derivative of the right side?
So this is the formula for average value. If I want to find the average value of f of x when it is 3x squared minus 2x on the interval from 1 to 4. All right, I want the average value. Well, we set up our integral from 1 to 4. We have our 3x squared minus 2x dx. But we're going to have to divide by 4 minus 1. So when we take the antiderivative, we can't forget our 1/3. You can put it up front if you want to, or you can put everything over that. But we're going to get, what do we get? X cubed minus x squared, and we evaluate that at 4 and at 1.
We're taking the antiderivative of 3x squared minus 2x?
Yes.
Okay.
Wait a minute, whoa. Oh, okay, that's why okay, so capital F means on the top part for the theorem.
Yes.
Means that you have to antiderive.
This is the antiderivative of this.
Wait, no, that's a good question.
This is the antiderivative.
Plus 1 over.
You add 1 to the exponent, and then you put 1 over the new exponent.
Yeah.
So if that's raised to the 1, 1 plus 1 is 2.
Over 2.
There used
Over
to be
two.
a 2 there, so canceled.
Cancellation is what I didn't see.
Cancellation.
I don't think that's a word.
God.
All right, so if we plug in,
Cancellation.
we're going to have 4 cubed is 64 minus 16 minus 1 minus 1. Oh, that's nice. So we have 64 minus 16, which is 48/3. So the average value of this function on the interval from 1 to 4 is 16. There's a big difference between average value and average rate of change. Average rate of change is that old slope function that we've been used to seeing. Average value, you always use an integral. Right? If you're looking for average rate of change, you plug into the function that you're given and do like the slope function. But if you want the average value, we use the integral. Yes, sir?
16 times 3 and you get the area.
Yes, that would give you the area. The area is 48, but the average value is 16 on that particular interval.
Wait a minute, why is
Let's look at when we have the integral from a to b of f of x. If we take this integral, do we get equation? Do we get a function? Do we get a number? What do we get?
No. You're always going to get
You get a number.
We're going to get a number because this is going to be equal to f of b minus f of a. Okay, so we will get a number. Let's consider this. If we say that f of x equals, pardon?
Doesn't it have to be on an interval in order for you to get a number?
We have to have a lower and an upper bound. But what if we're going from some constant a to x of f of t dt? What do you think might happen here? If a is a constant, are we going to get a number?
No.
Probably won't get a number. What will we get?
An equation?
Linear equation. A line.
Fraction.
A line, a
Slope.
fraction, a slope.
Function.
A function of what?
The height.
We're going to get a function in x here. Notice we're going from a constant to x. When we take the antiderivative and then we plug in x, we end up getting a function of x. Okay, let's look at an example. Let's say that f of x going from 0 to x of the sine of t dt. Let's see what happens here.
0. X is.
What do we get when we take the antiderivative? Negative cosine of t, and we're going to evaluate that at x and at 0. So Andrew, when I evaluate it at x, what do I get? If I evaluate this, if I use the fundamental theorem of calculus, I plug this in first, what do I get? Cosine x
Nice, Justin.
minus the cosine of 0. What is the cosine of 0? So here we're going to end up with a negative cosine x plus 1, or we can leave it like this. But notice here we get a function in x. It's no longer a function in t, it's a function in x. When we go from 0 to x, we get a function in x. All right, I'm going to... Okay, we want to take the antiderivative of this integral. So what do we get when we take the antiderivative of the sine t? Cosine t, and we're going to evaluate that at x cubed and at pi. So when we take the cosine of x cubed,
Cosine.
what's the cosine of pi? Negative 1. All right, so that's our function. Oops. And I forgot to switch it back.
Negative cosine x cubed minus 1.
Is it negative? Hang on.
Are you saying cosine or tangent?
Hang on.
What's the cosine of x cubed?
All right. Okay, so we get negative because the derivative of the cosine is negative sign. And so this becomes, this is minus again, isn't it?
So what's that little bar?
It's not negative cosine.
I forgot in your video. The whole bar. It's just saying it's.
That's where you evaluate.
Oh, that's the upper limit and the lower limit. I like to do, I think sometimes they may even put a little to establish your limits to remind you that you've got to evaluate at those limits. Okay, so here we get our function in x. Notice we started with a constant and we went to a function in x. Let's take the derivative of this function. All right, when we take the derivative, what do we get?
you just get what we just said?
Negative
It's gonna be sine x cubed. Sine x cubed.
3x squared.
Wait, wait, wait.
Wait, what?
You take, what's the derivative of the cosine?
Wait, I thought it was f of b minus f.
Hang on. We're taking the derivative, not the antiderivative.
Isn't it f of b minus f of
Do you feel like chain?
We'll have to use a chain rule.
Oh.
We don't do f of b minus f of a when we're taking a derivative.
I'm so lost.
3 cosine squared x negative sine.
Okay, let's think about this. What's the derivative of the cosine?
Sine. Negative sine.
Negative sine. So we're going to get the sine x cubed. What's the derivative of x cubed?
3 squared.
And what's the derivative of a negative 1? 0. Okay, so we get sine x cubed 3x squared, or 3x squared sine x cubed. We can just leave it that way. Oops. Now it won't let me do that. Okay. We can just leave it like this. 3x squared times sine x
So
cubed.
what you're asking us to do is to anti-derive it and then rederive it.
Yeah, but you have to give them the.
All right.
I understand.
Let me look at
I feel like
another.
questions like this can be worked on like at homework that we know to do.
Actually, I feel like we should just not do that anymore.
Wait, how do we take the antiderivative of sine t and then take the derivative of what we got? Make it into something else.
Pardon?
How do we take? Oh yeah, we did that. Never mind. I figured it out.
Okay, let's look at this one. Take the antiderivative. What do we get?
T 1/2 t squared plus 2t. 2t, yeah.
Justin, slow.
All right. And so when we plug in x, we get
X squared.
1/2 x squared plus 2x. When we plug in 0, we get. All right. Let's take the derivative of this. What do we get?
X plus
X
2.
plus 2.
That looks kind of like what we started with, doesn't it? What's the derivative of x? 1. Okay. Let's look at this one. This, can you see a relationship between 3x squared sine x cubed and sine t dt with that x cubed up there?
Oh, you multiply the x squared, x cubed, like substitute for the dt.
And then what?
Take the derivative of
Multiply it, you just solve it. Like,
And then you,
take the derivative of 3x and multiply it by that.
all right. Looks like you could substitute the x cubed for t, and then we take the derivative of x cubed, which is 3x squared. Here, we substituted x for t, and if we take the derivative of x, it's just 1, so we got x plus 2.
So does the lower bound matter?
The lower bound, notice in all of these, the lower bound was always a constant.
I'm guessing you're about to save us a lot of work.
This demonstrates for us, a lot of books call it the second fundamental theorem of calculus.
What was the first fundamental theorem?
F of a minus f of b.
What?
F of a minus.
What have we been doing, Joey?
Okay, the second fundamental,
Did I express that enough?
and when you're not here, you have opportunity to look at the book or look at RenWeb to see what it was we had in class.
I can't
That's-
learn just by reading.
You can?
Second from.
Really? Well, good luck in college, buddy.
Oh, very nice.
Then I suggest you be quiet, Joey, so you can learn by listening to your teacher. All right, the second fundamental theorem of calculus says that if you take the derivative of an antiderivative from a constant to some function of x, I hope I'm writing this right, f of t dt, that this is going to be equal to f of x dx. We just did it the long way, but the fundamental theorem of calculus lets us, I showed you that how it works every time, but the fundamental theorem of calculus allows us to just apply this, and then we don't have to go through the antiderivative and the derivative again. So if, yes, page 285, 49, 52, 63, 64, 69 to 90, every third, and 91.